this segment, we're going to talk about how we can use the TdS equations to calculate changes in entropy. And there's going to be a lot of derivation here, but don't panic too much. We're going through it to show you, to give you an appreciation for how we get the equations that we're finally going to get to, so you know what assumptions and what simplifications went into getting these equations. All right. So these equations are going to be valid for any process, reversible or irreversible. We're going to use them to calculate changes in entropy for an ideal gas, but they also are used to put together these thermodynamic tables that are in the back of your book. So the first thing we're going to do, we're going to look at an internally reversible process for a simple compressible system. And we're going to ignore kinetic and potential energy changes. So we've got Q minus W for a reversible process equals delta E, the change in entropy for a, or changes in energy for a process, which in this case would just be delta U. Or in differential form, I've got some differential amount of heat transfer minus some differential amount of work equals du. I'm going to handle that first one first. So the Clausius inequality gave me an equation that has that differential amount of heat transfer reversible process in it. So I'm going to just use that and put it in terms of TdS. And for the second guy, so this is the differential amount of work for a reversible process, and I've got an equation for that. It's the integral of PdV. So quasi-equilibrium, reversible, those are sort of interchangeable there. And so work is equal to the integral of PdV, but it's also equal to the integral of some differential amount of work integrated from one state to another. And so that differential amount of work is just PdV. And so now I've got my first TdS equation. I put things in terms of little s and little v and little u there. I've just divided through by mass, put it on a per mass basis. So now I'm going to rearrange things, put it in terms of ds, so just a little algebra there. And sometimes we like to use enthalpy, so what I'm going to do is I'm going to say, okay, well, dH is equal to du plus PdV plus VdP. And then I'm going to rearrange it, get an equation for du, and plug it into my TdS equation there. And you'll see I've got a couple of terms that'll just drop out. And there we go. Now I've got two TdS equations that I can mess with. So I'm almost there. Here we go. I've got two equations, two TdS equations, and I'm going to use these to calculate entropy changes for an ideal gas. So ideal gas obeys the ideal gas law, and I know I'm going to have to integrate these two things. So I need to get them in terms of something that I can integrate. So on the left-hand side, you see you've got P over T dV. I need to get P over T in terms of specific volume so that I'm able to integrate it later. So that's where my ideal gas law comes in. Now I need to do the same thing with the first term. So du over T, I need to get du in terms of T. So I'm going to use my equation or my definition for specific heat. And you could see this is in terms of a partial differential, but because you've got an ideal gas, which is only a function of temperature, I can get rid of that partial and just replace it with a regular differential. Then I just algebraically solve for du and plug that into my TdS equation. And I've got a little bit more useful equation. Now I'm going to do the same thing on the other side. So I'm going to put V over T in terms of pressure using my ideal gas law. I'm going to put dH in terms of temperature by using the definition for Cp. So I've got dH is equal to Cp dt. And now I've got my second equation. I'm almost there. All right, so here's my two TdS equations. Almost there. And I'm going to consider when I calculate delta S by integrating these two functions, I'm going to consider two cases. One is if I've got an ideal gas with constant specific heats, and if that's the case, then Cv is a constant, R is a constant, they both come out of the integral, and so the integral of 1 over something is just the natural log of that something at state 2 over the something at state 1. So you can see I've got things in terms of natural logs. Same thing over here. Cp and R are both constants. They come out of the integral. And there's my equation. There's my simplified equation. So those two equations are valid if you got an ideal gas with constant specific heats assumed. You got to make those two assumptions to do this. All right, now we're going to not assume specific heats are constant. So we're taking into consideration how Cp and Cv vary with temperature. All right, so I've got this equation here, and I've got two terms. I can integrate the second term pretty easily because R is just a constant, and that comes out of the integral, but that second term is a little bit more difficult. So what we're going to do is we're sort of going to divide this up into two functions, and I'm going to choose 0 Kelvin, so the little 0 with a little slash through it, that's 0, just because it's a convenient reference point. And now I've got two functions that are just a function of temperature, and I'm going to call each of those functions there S0. So S0 at state 2 would just be a function of T2, S0 at state 1 would just be a function of T1, and these properties here are tabulated in your ideal air tables. So that's those S0 values that are tabulated there. All right, so once you look those up, then you can come back here and you can plug that into your equation. So I've got S02 minus S01 minus R natural log of P2 over P1. So all of this derivation has led you to 3 usable equations. 2 of them you can use to evaluate changes in entropy for an ideal gas with constant specific heats assumed, and 1 of them is used if you don't make the assumption of specific heats being constant. So just keep in mind what assumptions that you're making, ideal gas for both of them, constant specific heats for those top 2. Keep in mind what assumptions you're making, and you'll be just fine. So if you got an ideal gas, these are the equations you got to use. If you've got something like water and maybe it doesn't behave as an ideal gas, then use your thermodynamic property tables. All right, well, I hope that was helpful. We'll do lots of practice problems the next time we meet so you get a good handle on all this. All right, thank you for watching.